Welcome back, guys. We're going to be talking about, we'll further more on our effective atomic number rule. So where we make use of the word, the neutral method. A quick recap on our previous lessons where we talk about the effective atomic number or the 18 electron rule. So this is just based on to determine the stabilities of organometallic complexes. That is how stable they are. So like it's just similar to that of when we discuss the noble gases. That is when they are fully filled shells, they are said to be stable. That is they are all reactive at that moment. So now like likes of neon, we say it has fully filled electron, it has 8, and furthermore, and when we discuss in terms of organometallic compounds, so that is to say when we talk about the 18 electron rules, it is just similar to that of the noble gases, that is to attain stability. So now when the organometallic compound consists of a metal to carbon bond, it can metal to double. So metal to carbon double bond, metal carbon single bond, or metal carbon triple bond. But now we have a metal being surrounded with ligands, that is the total electrons that must made up organic that must make it up to say this is said to be chemically stable. So it should attain 18 electrons. So now we have different kinds of methods in using the effective atomic number. We have different kinds. So the first one is the oxidation state of the method, and while the second one is the what is the neutral method. So now you consider here we consider the neutral method in this aspect. We consider the neutral method. So now under the neutral method, we talk about where we make use of where we make use of the valence electrons and the respective ligands in their neutral state. That is the respective ligands in their neutral state. So our first example, so this method use the numbers of electrons that will be donated by the ligands. That is, in this method, we make use of the number of electrons that will be donated by the ligands if they were neutral, if they were said to be neutral. So for neutral ligands such as our carbonyl, electrons are donated in the same way as in oxidation state method. So now for monoatomic ligands derived from ions, ligands are considered to donate the numbers of electrons equal to their negative charge as free ions. So for example, as free ions, we have C chlorine minus, O2 minus, and N3 minus. So the electrons counted by neutral ligands model, that is, so the numbers of electrons to be donated are for chlorine minus, it will donate 1 electron, right? For O2 minus, it will donate 2 electrons. So that is for N3 minus, it will donate to 3 electrons. So this is the meaning of the statement that ligands are considered to donate the numbers of electrons equal to their respective charge in their free ion. So they will donate the same electrons. So now to determine the total electron count by this method, one does not need to determine the oxidation state of the metal. So in this scenario, you don't need to determine the oxidation state of the metal before we can get the the stability, before we can get our 18 electron our 18 electron using the neutral method. So now the example before us, so we consider some few examples in this lessons. So the first one we have here is ClCl6. So you have heptacarbonyl chromate. So now, because the only ligand in this compound here, when we consider this compound, the only compound in this is the neutral CO. So the electron count by this method is identical to our oxidation state method. So now, the first phenomenon is to determine the valence electron of we have the chromate and we have the what carbonyl. So the best method is using the neutral method, determine the oxidation number of the the valence electron of the chromate. So now the valence electron for chromate is said to be what is 6. So that is this 6. So you can see it is 6. And our carbonite, the charge of carbonite is here is said to be what? Is 2. But don't forget, how many carbonite do we have? We have 6 carbonite. So that is, so 2 times what? 6. Summing up to what? To 12. So then the next thing is to what? Is to add it up. So 6 plus 12 is said to be what? 18. So here total we have what? 18 electrons. So this make our compound here to be what? To be stable. So they are said to be what? Chemically stable. So another example here we have is we have this. Another example is we have the haptic 5 of C5H5 FeCO2. So chlorine. So this is another example. So in this method, we have our CP. So this is our CP ligand. So I will make, so now this is the structure. Let me talk about it. This is the structure. So this is the structure. We have our Fe being sandwich. We have our chlorine. We have our carbonite. So this is the structure. We are told to determine the 18 electron rule of this compound. How stable they are. Is it chemically stable? So the first thing is that we've identified the various ligands. You can see we have a CP ligand, a cyclopentadiene, we have a chlorine, and we have 2 carbonite. So using the 18 electron rule, so we have Fe at 0 oxidation state. So that's why I said neutral method. Our metal will be in a 0 oxidation state. So the next one is our cyclopentadiene, which is N5C5H5. So the next ligand is we have 2 carbonite group. So after the 2 carbonite group, we also have our chlorine. So the total electron. So then let's start with our ion at 0 oxidation state. So the valence electron for ion is what? Is 8 electrons. Then for our cyclopentadiene, that is our hapticity 5, is said to have 5. Haptic 5 is said to have 5 electrons, and our carbonite usual is said to be 2. But how many carbonite do we have here? We have the charge for carbonite is said to be 2, but we have 2 carbonite in this scenario. So that is 2 times 2, making up 4 electrons. And chlorine is said to be will donate 1 electrons. So which is 1. So now the total sum of electrons in this organometallic compound is said to be 18 electrons. So with this we can simply say that this compound is said to obey the 18 electron rule. It's said to obey the 18 electron rule. So we'll consider some respective examples where there is a presence of of charges. Where there is presence of charge. So now let's discuss when there's presence of charge. So how do we go about it? So now, many organometallic complexes are charged. So they have charge, and this charge must be included. So in the scenario where you have organometallic complex, you are to determine the effective atomic number. So most of the organometallic complexes are charged. So and this charge must be included when determining the total electron. That is, the charge must be included whenever you are determining the total electron. So the charge must be included. So we can verify by either method. That is, we can verify by either method using the neutral method and the oxidation state method. So the first example to consider here is we have manganese. So this is our first example to consider. So we can see this has a charge outside the complex. We can see a charge. There is a presence of charge here. So then, that is, we must also consider the charge being present. First thing, before we calculate the effective atomic number. So is there presence of charge? Yes or no? So we can see there's the presence of charge here. So now, using the neutral state, the neutral method. So what are the we have our transition metal, our manganese. So they need to see, locate the numbers of ligand. We can see we have our carbonyl. So how many? This is the only ligand the neutral ligand being present. So we have 6. You can see we have 6 in total. So the next thing is that let's calculate, and don't forget there's a presence of we have 6 in total, and don't forget we have our charge also. We have our charge, so we have our plus charge also. We have our plus charge, so we need to include our charge. So when we are summing it up, so we need to include our charge. So now the first one, you already know that we are making use of the valence electrons of our manganese, which is 7 electrons, and our carbonyl, we have 6 carbonyl. We already know that the charge of carbonyl is said to be 2, so that is 2 times 6, making up what, 12 electrons. So you can see with this, how many charge do we have here? We already have 19. We already have 19. So don't forget, we have our charge outside the complex, which is our plus charge. So when we talk about plus in chemistry, that is mean subtract. So when we talk about plus in chemistry, we are talking about the loss of electron. So that is, so we subtract, that is subtract 1 electron for each plus charge. So that you subtract 1 electron for each. If it is plus 2, you subtract 2 electrons. If it is plus 3, you subtract 3 what, electrons. So making up what, total of 18 electrons. We can see we have a total sum of what, 18 electrons. We can see that this compound is said to obey the 18 electron what, rule. So the next example, so I think we understand this. So if you have any questions, you can drop it in the comment sections or DMs on WhatsApps. So now let's consider some respective examples in our charge method. So we have this. So we have our example here. So you can see outside our complex, we have a negative charge electrons. We have a negative charge electron. So we consider using our neutral method. So let's list out the complex. So first of all, we go with our transition metal, which is our chromium. Then we have our CP ligands. So we can see abscissity of 5. So we have our CP ligands. So the next one, we have our carbonyl. That is, we have 3 carbonyl. So we have our carbonyl. So you've seen we've successfully listed we've listed our ligands and our transition metal. So the next one is, don't forget the charge. We need to include this charge. We have a minus charge. So we have a minus charge. So then we need to add both of every single ligands together. So the first one is our chromate. So our chromium. So first one is our chromium. So what is the number of electrons? That's our d electrons. That is, it has 6 electrons. So it has 6 electrons. We already know that our cyclopentadiene has 5 electrons, and we have 3 carbonyl, and we have carbonyl as the numbers of charge it has is 2. So that is, now we have 3 here. So 3 times 2. So that's 6 electrons. So now we have a net charge of a minus net charge. So when we're talking about minus, that is, we add electrons for each charge. So that is, we add electrons for a minus charge. So we add electrons, that is 1 electron. So we add 1 electrons for a minus charge. So now summing up everything here, we have a total of what, 18 electrons. So this is a very simple aspect. So we've discussed when there's a charge being present, when there's a charge being what? Being present. So another one we need to discuss is our metal bonds. So we also discuss our metal bond. So that is when there is the presence of a metal bond. So for a metal bond is equivalent to an electron pair. It's also equivalent to what? An electron. I think we used something like this in our previous classes when we talk about, I think we have two manganese surrounded with quite numbers of our carbonyl group. So where we also make use of our metal bond. So now in the case where you have a metal bond, so it is equivalent to an electron what? Pair. So it is when you have something like this, it's also equivalent to what? An electron what? Pair. So in general, these electrons are assigned equally to the metal bond. So the electrons are equal to the metal bond. So using so for example, when we have a metal single bond and a metal double bond and a metal triple what? Bond, making use of our neutral method. So for a metal single bond, that's one electron, it is one electron, and for a metal double bond, that's two electrons per metal. So now for a metal triple bond, that's three electrons per what? Per metal. That's three electrons what? Per metal. So now a very good example of this, a very good example for our metal bond. So we'll make use of our previous example in our previous class. A very good example is our CO. So this is a very good example. So we have so let's list the transition metal and the ligands out. So we have our manganese, we have our carbonyl, which is we have 5. Then also we can see there's a presence of metal single bond. So a metal single bond which is present. So we can see which is present. So now for manganese, the valence electron is what? Is 7 electrons. For carbon we have 5. That is on each side. So we have 5. We can just pick one. So we have 5. So that's 5 times 2. That's 10 electrons. And don't forget, we need to include our metal. So the next one is to identify the metal being present. And is it a single bond? Is it a triple bond, or is it what? A double bond? So we can see this is a metal single bond. So that is the total number of electrons it carries what? Is what? 1 electron. So we have our total sum, which is what? 18 electrons. We can see that this organometallic compound obeys the what? Obeys the 18 electron rule, or our effective atomic number rule. So this is the end of our class. Like and subscribe to our YouTube channel. So thank you very much.